in labs, like tomorrow, what you guys do? Are they going to demonstrate that this is?
It's 5441 coming right now. Third over.
And the one that's most resistant to temperature is the 4.
All right. So question number 1, list 3 factors that can be used to control polymer crystallization. Yes.
Side groups.
What do you mean side groups?
Like you choose both your side groups, and it'll be more likely to crystallize due to interference with each other.
More likely to crystallize?
No, sorry. Less likely to crystallize because they will.
It's that can decrease. So you can so you can think about side group.
They'll just stuff like the ordered lattice.
You can think about bulkiness. Now, as I said last time, it doesn't mean you can't crystallize it, but it can make it more difficult. And I'm going to go ahead and put steric hindrance in there as well, which isn't necessarily something that you need a bulky side group for. Any other answers? So it's lots easier ones than that. Yeah?
Side chain orientation.
Chain orientation, what does that mean?
Like atactic or syntactic.
Well, now you just said 2 different things. So there's tacticity. Is that what you're talking about?
Yeah.
Yeah. All right. So that's a huge one because it's one of the easiest ones. Tacticity. Tacticity. I'm trouble spelling it. So atactic, isotactic, syndiotactic. All right, if it's all isotactic or all syndiotactic, it'll crystallize. If you start adding in atactic material or make it all atactic, then you can decrease the crystallization. What else? Temperature. What do you mean temperature?
Rate of cooling.
Rate of cooling. All right, that's a different thing than temperature. Yeah, all right. So rate of cooling. That is a very important one. Again, as I mentioned before, you take a hunk of metal and you cool it down at 3 million degrees a second, it's amorphous. All right, polymers are a lot easier to get there than metals because they are lousy thermal conductors. But if you make them very thin, then the heat can come out and you can make it amorphous, whereas it might be crystalline otherwise. What else? There's at least a couple more. Yeah.
Copolymer content.
All right, so we can talk about copolymerization. So I gave you some examples of that last time. We talked about crystallization, how it's measured by DSC. Anything else? Yeah?
The chain length, so like molecular weight.
To a certain degree, molecular weight, yeah. I wouldn't say that's the most efficient one, but yes. So chain ends are defects, and those chain ends don't get incorporated very easily, and for enough of them, then you can interfere with crystallization. Any others? That's pretty good. Any other thoughts? I mean, you can talk about molecular weight as being an example of defects. It doesn't have to be a chain end to be a defect. There are lots of other things, like chain branching, for example, is another example of defects. Okay. So hopefully that was useful. There are a lot of different ways of doing it. Some of them are practical than others. All right. So then on to question 2. What is toughness? And I know there's a legal definition that I saw a lot of. What's the legal definition? Yeah.
Resistance to fracture.
Oh, that's the non-legal definition. What's the other legal definition? Oh, come on. When you first learn right away. What? Area under the stress strain curve. All right, that's it. Area under stress and strain curve. And so it's a great example of an absolutely correct answer that is absolutely useless because you can't feel that. All right. So what's the other answer?
Resistance to fracture.
All right. Resistance to fracture, and usually we qualify that after damage of some kind. That's kind of what we think about when we talk about the hard materials view of toughness. Okay. Let's see, so how tough is water? Infinitely, okay? Water equals infinite toughness. So you can take a puddle of water and beat it to death all day, and then when you're done, it's still a puddle of water. All right, it hasn't fractured. Okay, it's still in one piece. Okay, so normally we think about polymers as being relatively tough. If they're amorphous, that makes them tougher. If they're crystalline, they're less tough. Okay, but absorbing fracture energy is a key part of what we want polymers to be able to do in many applications. The example I always like to give is what we talked about already. We talked about the racquetball or super ball or whatever. When it gets frozen below glass transition or goes below glass transition, it loses all its toughness. You drop it on the floor, it shatters. Above the glass transition, it starts out as a round sphere. It hits the ground. It deforms into a pancake shape. It doesn't like that. All right, it bounces back up and returns to its round self again. That's an example of a very tough material. That ability to deform, change its shape, and then rebound to assume the original shape is an indication of considerable toughness. Okay, and when we talk about composites, there we start to see good convergence between inorganic materials and organic materials. You're talking about damage to a structure and how the composite features in that structure help it resist that damage. Okay, are we clear on both of those definitions? You know, again, I'm obviously leaning toward the second one because that's the one that helps us think about impact strength primarily. All right, make sure your names are on those papers and please hand them forward.
We didn't talk about the second part.
Oh, I'm sorry. Yeah, you're right. How can we design a polymer to control? I kind of talked about it, but how do we design it? Yeah.
So I said, based on crystallinity, a more crystalline material will have more brittle fracture and will have lower toughness, where a more amorphous material will have a higher toughness.
Okay. Crystallinity and its relationship to amorphousness, basically. All right, so we can do that with this issue of working with toxicity, as you said. Any other examples? Yeah.
Increased undercooling.
Increased undercooling. Any others? All right, so we heard about molecular weight a minute ago. So if I take my polyethylene and I turn it into ethylene gas, it's pretty darn tough at that point. All right, molecular weight is a great way of increasing toughness if you can stomach the results as far as your application is concerned. So as it goes from being polyethylene to candle wax to chewing gum to a liquid to a gas, its toughness keeps going up, but you know, utility is starting to go down depending on what you're doing with it. Any other answers? Okay. So again, make sure your names are on those and hand them forward. Okay. Thank you. Thank you.
We've got some extras here.
Oh. All right, thanks. All right. So, picking up from last time, where I was talking about the modulated DSC and what that means for us. And so, if you recall, that means that we're not just increasing the temperature, we're increasing it and then letting it drop back down and then increasing it back up. So there's this incremental runga-kutta, you know, a little bit of heating at a time view followed by cooling of these types of polymers. And I wanted to give you a couple of examples to try to help amplify the utility of this. And so this is a kind of interesting thing, PET ABS blend. All right, and so polymer blends are actively being researched. There's a couple of places in technology where we might see them. Drink containers is one that comes to mind. But in many ways, blends don't always work out as well as we'd like them to. But in this context, examining this particular blend, which polyethylene terephthalate recycling number 1. Oh, much better. And then we have something that sounds exotic, acrylonitrile butadiene styrene, ABS. Anybody know what ABS is used for? Yeah.
Some car parts and stuff.
Some car parts, absolutely. Very important car parts. I do 3D printing of ABS. Anybody else? Yeah. I think that's right, yeah. I think Legos are made from ABS, yeah. I should check that one out. I think it was either that or polypropylene. But, and so one of the reasons why it makes sense for Legos, so ABS used to be used a lot to make landline phones. All right, that historically landline phones, the old ones, before we went to cell phones, which aren't ABS, were all ABS construction, which is because you could throw it across the room and drop it off of a building and it bounced, all right? Refrigerator parts, the interiors of refrigerators are often ABS as well. And it's because of that toughness, that ability to withstand these impacts. ABS is very good at it. So they're blending these two together, and what you see in normal DSC is what's shown here in the middle, where it goes down, then we see this increase. First off, we have to know that this is PET, and PET does this weird thing called cold crystallization, where in the amorphous state, it spontaneously crystallizes. And then we heat it up further, and that crystallinity can melt. That's off the chart of this graph. But what we're seeing in the middle here is evidence of that. And so what we do then is run modulated DSC, which rather than just heating it up and looking at the heat output, heats up, cools back down, heats up, cools back down. And so on top we see the non-reversing component of that, and that means something that as you heat up evolves or absorbs heat, and then you cool it back down and it doesn't change structure. And we see that here in this cold crystallization process. All right, so PET is doing what it's supposed to do. It's cold crystallizing, and so you have peak associated with that, and as we cool off, the crystals don't dissolve or melt or something because we're cooling it off. They're less likely to melt or anything. So that is a non-reversing feature. On the other hand, below this we have the reversing component, which does respond to cooling, and in this context, the glass transition of PET at around whatever that is, 72 C, is reversing. You know, heat it up, cool down, it gets glassy, amorphous, viscoelastic amorphous, goes through that change as temperature goes up and down. And then the other thing that's happening here is we also see the glass transition for the ABS, which in pure form is 104 or more or less. And so we see both of those things in the reversing component of this. The important part of this is that, and this is where this particular version of DSC really shines, is it separates things that are on top of each other. So it's separating the crystallization of PET and the glass transition of ABS. Without that, in the middle there, they're on top of each other. You can't even see the glass transition of ABS because there's just all this energy associated with cold crystallization of PET. Okay, hopefully that makes sense. Any questions about that? Another example here is another blend. So we have polyethylene, we have polycarbonate, which we haven't talked about, but a lot of us wear on our faces, all right? And then PET. So the PET, you already know, cold crystallization is going to be part of this discussion. So we have, again, the total showing us lots of different things going on. We have the cold crystallization and then this sudden drop. All right, and this is again a great example of how teasing out the reversing and non-reversing is useful. And so the non-reversing shows us this cold crystallization for PET. But then if we go back and look at the reversing components, again we see the glass transition for PET, relatively low temperatures. And then we see, in this context, the energy associated with the melting of the polyethylene component. Polyethylene is recycling number 2. All right, and then if we go up to higher temperatures, we also see a glass transition for polycarbonate. Okay, but again, where everything overlaps, if we just had the red curve, then we wouldn't know what the heck is going on. All right, but with the reversing and non-reversing separated out, we know that part of that is crystallization, the other part of it's melting, both of which are more or less occurring in the same thermal space.
So the red curve is like melting?
The red curve is normal DSC, okay, where everything runs together. And the green curve is the non-reversing, the blue curve is the reversing, and that separates things out, all of which are making up the red curve. But here we break them into two different thermal behaviors. Any questions about that? So hopefully we can see why this modulated DSC is useful. And understand it as well. Heating up, cooling down, heating up, cooling down. It sounds laborious, but the machines do it really well. Okay. Okay, so then we're going to move on to additives. And as I said before, additives are a very important part of plastics. They're arguably, why plastics are useful in many different circumstances. And what this image is showing you is a TEM of what's called flame-made amorphous calcium carbonate on the left-hand side. That's a 20 nanometer bar, so those are pretty small particles. And then we also have calcium phosphate nanoparticles on the right. That's a 50 nanometer bar, so these are also very small particles. And it makes a comment of how the structure resembles fumed silica. So we can get these additives, and the ultimate particle size is very, very small. And so this is important to us because we think about trying to transfer things between these phases. And so in these cases, what we're talking about here are things that are inert, meaning that they don't chemically react. They physically interact, of course, but there's no chemical reaction in these structures. And what they can do, just by rule of mixtures, is increase the stiffness and hardness of a plastic. And that's what's kind of shown over here. This is just clay, dug out of the ground clay, which has the advantage of being cheap. All right, and it's also an inorganic mineral, meaning that it's a harder, denser, stiffer material than the polyethylene you might put it in. So this is part of the origin story for additives in plastics. When they first started making plastics, they realized they could sweep dirt up off the floor, add it to the plastic, and some of these properties would go up, and the cost of it would go down because it's just dirt off the floor. So things that are like $1 a pound, clays, talcs, barium sulfate, as it says here, are common things that can be added to these plastics to both make them go farther by increasing the volume, but also, and this is initially very much a secondary thing, end up with better properties. So again, these reduce the cost of the overall compound as they're generally cheaper than the base polymer. You know, we're used to think about plastics as being cheap, but these things, add to them, at least in this context, these are even cheaper than the plastic. All right? So hopefully that's... But you dig into the nitty-gritty, and things like particle shape and size are both going to be important in this context. And so if you have, I just showed you a nice bunch of round particles, but if you have like a plate-like particle or a needle-like particle, they don't mix very well, all right? Or maybe a star-shaped particle, something like that. You're not going to get very good mixing. And you also want the size to be pretty small. Smaller particles give higher values of properties. So if I mix, you know, I have a nanoplatelet of clay that's, you know, a fraction of, well, I guess a few nanometers on an edge and a few nanometers thick. I mix that into the polymer, then I'm going to get good interaction of the properties of that clay with the polymer. But if I have a, you know, piece of clay the size of my fist and I try to mix that into a polyethylene, it's not going to do a great job of mixing or imparting properties to that. And so in general, though, you get higher values of properties, including tensile strength, heat deflection temperature, which we've talked about, and this should also logically relate to creep in your minds because they're pretty much the same thing. Modulus is going to increase and hardness is going to increase, and where things go off the rails sometimes is in toughness. You may think, and a lot of people used to think this, that whatever you add to the polymer is going to increase its toughness. But here's where things can go wrong because clay or talc or these minerals are not very tough. And the only way you can get them to increase the toughness is by really decreasing their particle sizes. So a lot of people spend a lot of time working on nanocomposites thinking that, oh, the toughness is going to go up, and it didn't. In many cases it stayed the same, and in other cases it went down when you added these nanoparticles to the polymer. But in general, tensile strength, heat deflection temperature, creep, modulus, and hardness are all just going to increase. need to think about the nature of how you measure these things. It should make sense to you that something like hardness especially is going to increase when you put these inorganics into this polymeric matrix. Too coarse particles can result in lower strength than the unfilled plastic. As I said, we saw this a lot in the rush to make nanocomposites. Generally, however, even the cheapest or most filling additives increase plastic strength and heat resistance. All right, and so we've talked about inorganics. One of the other things they did, they took like wood flour and sawdust and all kinds of things and threw them into plastics at the very beginning. That last longer, be a little more property rich, but mainly it was to make money. Okay, so it's not just any old additive, it's not just any old particle size or shape. Those have to be engineered. And so we can get this perfect rule of mixtures behaviors. You guys know what rule of mixtures is, right? One side of the curve, other side of the curve, and between them it's supposed to be linear or at least within a certain area. And so this is typically true for properties, again, hardness, compressive modulus, heat deflection temperature, creep. However, these usually do not apply to toughness. In many cases, it may not apply to tensile strength. I just got through telling you that it does. Sometimes it doesn't. Impact strength is another one where we can have problems because impact strength, as we just got through talking about, relates to toughness. The ability to survive damage and stay in one piece. And this can be a problem. And what we can think about is something called an intensity factor that helps us explain this, which is defined, it refers to the ability of the polymer additive interface to cause chemical and or physical bonding. So what does that mean? If I have this additive, and I'm just going to call it an inorganic additive. And this can be a variety of sizes. It can be 10 nanometers, it can be 10 microns. The issues are all the same. And around this we have a polymer, again using the spaghetti representation. I don't want this to look like a flower, but anyway, it's a bunch of polymer chains around that inorganic additive. And so we know we need to have good stress transfer, and what we'd really, really like to have is more than just polymer chain in the same area. We want that polymer chain to interact with the surface as much as possible. And if we don't, and this is certainly true for a lot of different additives, if you don't, you can end up with an air pocket. Just air sitting there in between the polymer and the inorganic surface, and you have no load transfer. So that load transfer is created by the polymer chains chemically interacting with that inorganic surface. And one of the things that is annoying about this system is that polymers are organic, inorganics are inorganics, and they typically don't like each other very much. Like dissolves like, these guys are the opposite of each other. One's hydrophilic, the other's hydrophobic. They don't like each other much at all. You take polyethylene, put it on a piece of glass, heat up the polyethylene, it'll turn into a ball and sit on top of that glass. It won't wet the surface. It does not like it. And so in the extreme case, if you don't moderate that issue, then you end up with an air pocket, and instead of a composite load transfer improved properties, you've created a hole in your plastic the same size as that particle. All right, and all your properties you're trying to increase, you have instead decreased. All right, so this issue of the chemical interface is something that needs to be very tightly controlled. It's true for inorganic composites as well. Typically it's more of an issue for inorganic composites, but for organic composites it's also important. Any questions about that? Yes?
So is that one of the reasons why size is a big factor, is because there's more chances for the air pockets to form on a larger particle?
Yeah, that can be true. Right, you can get not as good chemical mixing when the particle sizes are larger because there's more opportunities to trap air. Yeah, that's a good point. Any other questions? All right, and so these reinforcing additives are part of the reasons why there's been such a growth in plastics as metal replacements. And so, you know, we have replaced aluminum in the 767 with these composites because we have a polymer matrix and engineered inorganic reinforcements of that polymer matrix that gave us something that's lighter than aluminum. All right, and so this is a great example of how that's happened. They have some disadvantages in comparison. They tend to have low rigidity, but of course if we reinforce them with something that's rigid, then we can balance that out. Tensile strength by itself is weak, but again, you add a high strength carbon fiber to that polymer, and now it's not such a low strength material anymore. High thermal expansion coefficients, this can be an issue, but you know, again, rule of mixture says you put enough fiber into it, you start to overcome some of that. Water absorption is something that can continue to be an issue, especially in composites. We have talked about examples of low maximum surface temperature, but as you saw on that table for the polypropylene and the nylon way back a few lectures ago, you know, you can get the heat deflection temperature to go up to the melting point of the plastic, basically by reinforcing it. So you can really change that. Impact strength, that can be a problem for both the plastic and the reinforcing matrix. Hardness and scratch resistance and creep resistance, you know, some of which can be partly overcome by what you reinforce it with. So if we add glass fibers, as that table from before will tell you, glass fibers can improve a lot of this because they average out the properties they bring to the table along with the matrix that they sit in. For example, glass fiber reinforced polypropylene has 3 times the tensile strength and 4 times the rigidity at room temperature versus unfilled polypropylene. Okay, so big changes in these properties, and this increases to 4 and 8 times respectively at 100 degrees centigrade. So we're really increasing these properties even at higher temperatures. So it overcomes a lot of the associated with the limitations of these plastic materials. Any questions about that so far? So we talk a lot about fibers because that's the high-tech, really splashy applications of composites. But there are other examples in which we don't have to have these nicely oriented fibers, which, you know, it sounds great, it's kind of a pain in the ass to do, but anyway, when you can do it and it's necessary, you can go through the struggle of doing that. But we can have other examples of unoriented materials, and these can improve the strength if it's engineered correctly, and in many cases can greatly increase the tensile properties. And I want to show you this one example that is important because it's, I wouldn't say it's all around us, but it's frequently encountered. This is called high impact polystyrene. And so what do we know about polystyrene? It's hard, it's rigid, it's got a high modulus, which means that it can be sensitive to being dropped on the floor in pure form. Polystyrene can shatter if you drop it on the floor. And what has been made is what's called HIPS, is this process of adding rubber particles to polystyrene. And it turns out that if you see pure polystyrene, I don't mean styrofoam, I mean a pure hunk of polystyrene, it's probably HIPS polystyrene. Why? Because it just makes the most sense when it comes to making polystyrene that has some kind of structural application. And so you're taking these, as it says here, micron-sized rubber particles. You may be thinking, oh, why would you put black particles into polystyrene? It's not what's in your tires, okay? Why is rubber in your tires black? Anybody know? What is it that makes rubber black? No, it doesn't. It doesn't give it that distinct color. It can go in that direction, but that's not all the way. Okay, so rubber is black because it's got carbon black in it. Okay, which makes it wear better. That's why carbon black was added. And in fact, when they first came out with rubber tires, way back the 20s, they were white because that's what the native color of rubber actually is. Even from the stupid rubber tree, it's white. Yes?
Is that why you get the tires with the white insides and the black outsides?
Yeah, the white walls are made with rubber that doesn't have carbon black in it. Yeah, okay. And so we're doing the same thing here. We're working with tiny rubber particles that, as it turns out, don't have to be black. And we're reinforcing this polystyrene with them. And if we start at At 0% rubber, we get the classic stress strain curve, small area under the curve, so not very tough material. We add in 10%, 20%, 25%, we start to really increase that area, and we have obviously a situation in which that polystyrene can now respond to the applied stress and strain to greater and greater levels. If we go to 100% rubber, then we're at 600, 700%. Okay, so clearly this is a rule of mixtures arrangement. But it does also require that there's a good interface between these two phases. We'll talk more about that later on in the class. But anyway, so HIPS is something that when we think of clear polystyrene, it's HIPS polystyrene. We don't call it that anymore just because it's everywhere now. But it is rubber toughened. Any questions about that? And even in these unoriented systems, we also have to worry about this interfacial control. And you might think that polystyrene and rubber, they're both organics, they should mingle well. It's not that easy. This is another example of that, in which we take polyethylene and polystyrene and blend them together, which it's kind of doesn't make a lot of sense, but if you mix polystyrene and polyethylene together, you might think they should like each other. They're both these non-oxygen containing polymer phases, but it turns out they tend to phase separate. So you mix them up at a high temperature, looks great, start cooling it down, polyethylene and polystyrene phase separate from each other, and you get complete separation of those two. And so this is a problem because you've taken that polystyrene and you've reinforced it with polyethylene particle-sized holes in the polystyrene, which is really bad for polystyrene, which is already brittle to begin with. Now you've made all these huge flaws. We know what critical flaws are, right? And how those affect properties. This is a great example. This is why we think of all plastics as Griffith solids, because they're very sensitive to flaws, like many ceramics and glasses. Similar issues, not as bad, but similar issues. And so obviously this is an example where you tried to make it better and you made it worse instead of better. Okay? And so what can be done is a very nice change to the composition, in which we look at a polystyrene polyethylene blend with 0.5 weight percent diblock copolymer. And this is what I'm showing up here. Let's scratch out that double bond. It's not supposed to be there. Okay. All right, so what we've got is a copolymer that consists of both polystyrene, and up here we have polyethylene, and then back down here we have more polystyrene. What does that mean? It means we have an additive that likes being in both phases. Okay? So instead of this complete and total separation that we see up here, if we go to 0.5% of this diblock copolymer, you start to see these tiny connections running across between the phases. All right, that's 0.5 weight percent. If we instead crank it up to 5 weight percent, the interface disappears completely. They no longer phase separate from each other. Okay, so the additives can be used to control the nature of that interface, and in controlling the nature of the interface, you can change the properties from being worse than they were before to being better than they were before. All right, any questions about that? Okay, and so the key part of this that makes a composite a good idea versus a bad idea, especially when we talk about load transfer, is how well that interface is designed. And so this is the main mechanism by which polymers are reinforced, so that they have better properties rather than worse properties. Inorganic reinforcements are typically not wetted by polymers, even at high temperatures. This can be a problem. The chemical bonding is poor, and as you saw before, if we trap air, then we have limited bonding and we decrease the properties. So obviously this is a real issue. And so similar to what we just talked about where we added in this copolymer, we add in other features or other compounds, and this is again why polymers in the reinforced case are also not very pure. And these things are called coupling agents, and it's not something that you hear about very much, but it's very widely used in all types of reinforcements. And so there are entire books given on coupling agents, and I used to get emails inviting me to conferences on coupling agents. It's this whole subfield that's really, really important in this area of plastic design. And so what these coupling agents consist of, if we go back to this is our inorganic again. which I'm not doing a great job of writing. Inorganic reinforcement. And so it's an oxide, let's say, okay? And so oxide surfaces consist of alumina or silica or something like that. What else do they have on their surfaces? Are they just nice, clean oxide? No. So what might I find on a surface, an oxide surface, like glass, for example?
Other ions?
Some ions, yeah, but something easier to get than ions.
Oils?
No, even easier than that, although that's possible too. Water, all right? So that glass in the back of the room has a thin film of water on its surface, all right, because it likes water, all right? So that's a consequence of the fact that there's an affinity there that we don't necessarily have with polymers. And so what we'll see on these surfaces is typically a lot of OH groups. And this is one of the reasons why polymers and inorganics don't like each other very much. Because with polyethylene, you don't have any of that, right? Polystyrene, we don't have any of that. And so what's done is you design a structure that is carbon containing and well, let me just go ahead and delete that. And this is being surrounded by, let's just make it polyethylene, for example, just to make it as simple as possible. So what have we done? We've created this thing called a coupling agent in green here, and this has on its ends, it's got a carbonyl oxygen and it's got a hydroxyl oxygen, both of which can now form what type of bonds with that surface? What?
Hydrogen.
Hydrogen bonds. All right. Strongest van der Waals bonds we know. All right, so now we've created something that has an affinity for that surface and can, because it's attracted to it, allow the rest of this structure, which is a CH2X. X can be 10, it can be 20, it can be a relatively long length of polyethylene, and then we're asking it to mix with the polyethylene around it. Not a problem. Okay? So by adding a relatively small amount of these coupling agents to the surface of these particles, we've now created an absence of interface. We've displaced all the air because these two phases can now like each other, quote unquote. All right, does that make sense? And now this process of load transfer is going to be enabled because we now have a strong interface. All right, so we get to what we were trying to get to before when I was drawing that other cartoon. Now, this is not the only coupling agent out there, and there's lots of these types of coupling agents, but there's other more refined coupling agents that don't just rely on hydrogen bonding. And these are examples of a direct chemical bonding called silane coupling agents. And we're just going to go over this briefly, but just to give you an idea of what is done here. And again, there's whole books written on this. Titanium-based coupling agents, there's silicon-based coupling agents. In this context, we're looking at an iron oxide nanoparticle. There's lots of potential applications for that. Tiny pieces of iron oxide, and like alumina or silica, they have hydroxyl groups on their surfaces, just like before. And what we do is we bring in these silane groups, and these are important. And this name is unusual, but they're important because they have silicon, and then they have oxygen. In this case, bonded to methyl groups. And what that means is these guys can interact and chemically react with those guys. Okay? So now we're forming a covalent bond to the particle surface. So this tells you how important it is that they use these types of chemistries to make sure you have a very good strong bond. And in doing so, you form methanol that goes off and is pulled out of the system. And now you have an actual metal-oxygen-metal bond between that coupling agent and the surface. And then, of course, along for the ride is all this stuff, which would be good for example, this would be great for interacting with polymethyl methacrylate. Be a great coupling agent for polymethyl methacrylate. It's got all the same stuff that PMMA has it. or maybe even PET could work pretty well with that. All right. So you design your coupling agent around the matrix that you're trying to put around that particle. Okay. Any questions about that? No, these can condense further, by the way. That's what this is showing. They condense with each other and makes the bond even stronger.
So what do these actually do to the polymer when they're added to it?
They are added to the surface of the particle, and then the particle with that on the surface is added to the polymer.
To make them have more interaction with the polymer.
To make them wet, exactly. And then once wetting also implies that molecularly they're also mixing at the interface, which means low transfer is good. Yes?
These coupling agents be like a soap then?
Stearic acid is an example of a soap, yeah, and that also has been used as coupling agents. Yes, exactly. So you're thinking of what, stearic acid and butyric acid? What?
Dishwashing soap, use it to get oil off your hands.
Yeah, yeah. So stearic acid and soap does the same thing. It's a surfactant, but in water, in that case. Okay. So we have, because it's so important, we have general expressions for interfacial control for a group of spherical particles, and one of the simplest ones is shown here. There are more complicated ones that are like a page long, so I don't show those to you. Just give you this one example where this sigma sub u is the strength of the overall composite. So obviously we're designing for strength. Sigma sub m is the strength of the unreinforced matrix, so we want to be better than that, right? And then phi sub f is a volume fraction of the filler, typically less than 35%. More filler is not necessarily better, all right? So, you know, a few percent, yeah, you can increase the toughness. You go above 35%, the toughness is going down. There's too much filler, okay? R is an interfacial factor, typically around 2.66, which is equal to the inverse strength of the matrix filler bond. How strong that interface is, whether there's a coupling agent there or not, determines what the value of R is. And so we see that for this given values of R, this interfacial factor, that we start out high and eventually it starts to drift down and become low. We can make the strength of the composite get lower and lower and become less than that of the matrix itself if we keep going off in this direction. All right, so the strength of this interface has to start at a relatively good value to stay above sigma sub m, but if it gets to be too strong, then it can go below sigma sub m. Okay. Okay. Any other questions about that? So this interface is really important to us. So I'm going to talk very quickly about a couple of other additives. And this relates to the fact that these are plastics. And plastics, we don't talk about it much, are prone to oxidizing, reacting. They're not high temperature materials at all, so lots of things can happen at relatively benign conditions that change them chemically. And so this necessitates the need for various types of stabilizers, because even at room temperature, plastics can be degraded by the heat present, light or UV around, and oxygen. And the best example is one we've already talked about. Oops, that's not what I wanted to do. Anyway, it's supposed to be a 3. I apologize for my crappy drawing. What polymer is this? Recycling number?
5.
All right. So we have this material, and it's sitting out in your backyard. It makes up a swing set or some type of palace or something like that your parents bought for you. It's sitting out in the backyard, and because it's in the backyard 365 days a year, it sees lots of sunlight. Billions and billions of photons are raining down on that surface all the time. It's not like you and me where the skin dies and sloughs off. It doesn't have the ability to replace its surface, okay? It doesn't grow any kind of protection. So what can happen is those photons go into the polymer and they make it vibrate. It takes that photon energy and transfers it into heat, all right? And in doing so, it can activate this carbon-carbon bond in the structure, okay? So they can become chemically reactive. And so what that means is we can start breaking these chemical bonds, and when we break them, we form this empty bond, all right, this free radical. So it consists of a single electron because it's broken off from its neighbors. And its neighbor's still there. It's also got this free radical. So in many cases, those guys might find each other and bond back up again, and everything's fine, all right? But, especially when you have billions of photons and you have other stuff around. So you have water, we have oxygen, we have formic acid, we have all kinds of things sitting out there in the backyard, all right? And so any one of those can jump in here and start to create new chemistry. And so one example of where this could go especially if it's water, which is a likely thing to happen, is you start forming OH bonds. All right, so what we've done is we've taken polypropylene, we've broken it, we've added OH to it. So this has done a couple of things. One, it's decreased the molecular weight. All right, and then also we've changed the chemistry. All right, so if you take one really long chain and break it, not a big deal. Break it 100 times, starts to be a big deal. But what's maybe more important as far as your stuff in the backyard is we've added a lot of secondary bonding that wasn't there before. So now it's no longer just carbon and hydrogen, it's oxygen and hydrogen, which means we can get hydrogen bonds between these different polymers, and over time your swing set becomes brittle and it breaks at some point, all right, because of this damage from the sun, this energetics imparted to the solid from the sun. Does that make sense? So it's not only degradation of molecular weight, which very definitely does occur, but it's also a change from purely dispersion type bonding to hydrogen bonding. All right, so yes, tensile strength goes up, but also the brittleness does as well. Okay. All right, so how do we get around this? What do we do? Of course, we go back to additives. That's what we're talking about here, is more additives. You can never have enough additives in plastics. And one example of this is this structure, which is phenyl salicylate. Which can be mixed into polypropylene. So what does this do? What's it doing to achieve our goals for polypropylene? So again, those photons from the sun come raining down by the billions onto this material, this polypropylene. And what happens is the best way of thinking about it is that these structures overall kind of act like a catcher's mitt, all right? And they absorb more of the photons than the polypropylene around it. And so in doing so, it transfers that light energy into vibration of the overall structure. And so you've got this heating up process, but you've also got a conversion of photons to thermal energy captured by these particular structures. We'll see this again when we talk about some colorants. They do the same thing. They take one light and convert it into a different wavelength of light. Here we're taking light and converting it into thermal energy. So it starts to vibrate the phenyl salicylate, and eventually that leaves, all right? But in doing so, what it's done is it's shielded the polypropylene from these photons, meaning that it can last longer when this is present versus when it's not present. Okay? So again, one of these invisible additives that makes up all polypropylene that we know of. It's necessary for this particular purpose. It's invisible to you and me, but it's always there. All right, any questions? If not, I'll see you guys on Friday, okay? The graded quizzes are up here.